next session with Philip from Akamai. He's a principal RAM distiller, and he will tell us how to use Julia for this anomaly detection pipeline. Right?
All right.
Anomaly.
Yeah, anomaly detection. All right. Well, hi everyone. Still a few people coming in, but thank you for being here, especially because there are 6 other talks happening at this time, which are all pretty awesome. There's also a BOF. So thank you for choosing my talk over all of the others. My name is Philip, and I work at Akamai. In case you don't know, Akamai is primarily a CDN. We run about 90% of the internet traffic through our servers. My team works on a product called mPulse. It does real user measurement, so we collect performance data from users as they browse our customers' websites. And we've been using Julia to do parts of this analysis since Julia was version 0.2. It's quite a while ago. I live in Cambridge in the United States, not in England. This is not Cambridge. This is Boston when you're standing in Cambridge, right? Boston has more lights at night, so it looks better at nighttime pictures. I bake bread. Sometimes I take part in competitions, and I have never won, but my scores have been slowly increasing. This one is my competition bread, which I think fell right in the middle. Now, bread is handmade, and the way it grows depends on 2 microorganisms, yeast and lactic acid bacteria, one for rising it, one for giving it flavor. And you have to get the balance just right to actually have a good loaf. But also because of this dependence on microorganisms, because of its handmade nature, because there's water in it which evaporates when you put it in heat, the final product is not determinable by things when you start out. So you don't exactly know what it's going to look like, how much it's going to weigh, etc. when it comes out. You just have to hope you get the best. And so that actually brings me to an interesting story. It's very relevant to this talk, as the curious case of the abnormal loaves. Right, so let's see. I want to tell the story. I don't know if it's true or not, right? But it was fairly interesting to me with the statistics background and the baking background. So I wanted to bring it up. After World War I, in Germany, bread was rationed. So you could get 1 loaf of 1 kilogram each, and that was your ration. So now, because of this handmade process, a 1 kilogram loaf is not exactly going to be 1 kilogram. Sometimes it'll be less, sometimes it'll be more. In fact, it follows a normal distribution. If you take all of the loaves baked in one day and you measured their mass, they would fall on a normal distribution of mass, and the center should be 1 kilogram. The median or the mean, in case of a normal distribution, they're the same. So this mathematician, a math professor somewhere in Germany, I don't know the city, decided to measure the loaves that he was receiving every day. And it turns out it was a normal distribution, but the median was not 1 kilogram. It was below 1 kilogram. And so he hypothesized that the baker was probably stealing some dough from every loaf to make a few extra loaves for himself or his friends or something like that. And so he confronted the baker and said, hey, your process is wrong, or you're doing something wrong. So the baker essentially adjusted his process, and now when the mathematician started measuring the loaves, every one of them was more than 1 kilogram. So problem solved, right? It turns out not quite, because when he looked at the distribution, right here, you see that it's no longer a normal distribution. It is the right-hand side of a normal distribution. So knowing the distribution, he could tell that the baker wasn't actually fixing his process. He was just making sure that he was only delivering the heavy loaves to the mathematician and the light loaves to everyone else. So essentially gaming the system by fixing what is measured and not fixing everything else. So by knowing the distribution, he knew that there was an anomaly here and that the fix was not actually fixing the problem. It was just fixing the measurement of the problem. So the lesson for me here is understanding statistics and the expected distribution of your data is important to anomaly detection. And luckily, Julia is very good at doing distributions and fitting data to distributions and knowing whether things match or not. So a lot of hypothesis testing is all good in Julia. So mPulse, kind of the same, right? Only we use web performance data instead of the mass of bread. So I'm going to very quickly give some background on mPulse because I'm guessing most people here do not have a web performance background or have never seen mPulse before. What we do is we collect web performance data. There's a JavaScript library called Boomerang that sits inside the web page of our customer sites. So we don't have a site. Well, we have a site, but nobody uses our site. Our customers have websites, and they put our JavaScript on their website. As a user browses their website, it measures how long it takes for the page to load up, and it sends that information back to our server. So there's no personal information about the user, just the performance of that browsing experience. And that's beacon back to our performance analytics application. It's called mPulse. It's written in Java, but there's also a Julia interface to it called mpulseapi.jl. You can package add that. It's in the registry. The data in the Java process is clean, filtered, sorted, and then it's streamed to various backend services. So one of them is our data warehouse where it'll be stored for a longer term. Other parts do anomaly alerting, visualization, and then there's also a Julia backend which has advanced data analysis and some amount of visualization. So at a high level, this is kind of what this looked like before we added the anomaly detection component. Right, so the website users up there, Boomerang is written in JavaScript. mPulse and the stream processing are written in Java. This advanced analytics component is written in Julia. And we hope the end users are human, right? With the paying ones, the customers there, we know for a fact whether they are human or not. They do have automated jobs, so there will be bots. With the end user using the website, we don't know that for a fact, so we have some kind of bot detection. Again, anomaly detection plays a big part in knowing whether the user using the web is a bot or human. Right. So in terms of the timeline, just to give an idea of the maturity of the project and why not everything is written in Julia, because if I looked at it now, I'd say everything except the JavaScript part could have been written in Julia. But we started in 2010. Julia didn't really exist at that time. Right? I publicly released Boomerang just to collect web performance data. There was no backend for it, so you would install it on your own site. You would collect data in your HTTP access logs and do something with it. In 2011, we built a precursor to mPulse. At that time, it was in Node.js, but we quickly moved to Java and sort of scaled it out both vertically and horizontally. In 2014, we added the advanced analytics capabilities in Julia. And at that time, Julia was 0.2. So things were changing very quickly with Julia, but our code base was fairly small. So we started with 0.2 and we migrated to 0.3 and 0.4 by 2015. So just in 1 year, we actually migrated our code twice to 2 versions of Julia. Then we kind of got stuck because we started adding all of this code. In 2016, we added this anomaly detection component, which is what I'm talking about today. And the number of customers that wanted that feature was quite a lot. So there were a lot of people dependent on the Julia code now, and we could no longer upgrade. So we were stuck on version 0.4 until 2023. That's last year, right? To give you some context, 1.0 came out several years ago. 1.6 came out several years ago. That's a long-term support. In fact, 1.6, as of this conference was announced, will no longer be long-term support because 1.10 will be. So I have a talk tomorrow about just the migration process. But in the feature is kind of a year old, but it's also been maturing over several years. The data we collect is mostly time series, so multiple users requesting web pages. We get performance data, we get beacon volume data. It's related to real user experiences. Each data point has multiple events. So in all, there might be about 500 different dimensions and metrics on the beacon. And it's like, when did the first byte come in? When did the first large thing on the page get drawn? When did the page complete loading? When the user interacted with the page, how much time before the interaction actually did something on the page to not frustrate the user. Because they're real users, it's an uncontrolled environment, kind of like the yeast and lactic acid bacteria. They're doing all sorts of things. Different users do different things. They have different kinds of devices. Their devices have different kinds of things installed on them. And so we can't know what the environment is like. We just have to look at what the expected distributions would be and try and figure out whether things are going normally or not. But because we have all of this data, we can render individual waterfalls. So this is a waterfall of one single page. This is a fairly simple visualization based on the data we have. It's done in the Java application. But we can also do multiple waterfalls. So we combine, in this case, about 1,000,000 different waterfalls into one. And for this kind of analytics, you need Julia. So it's much slower, but largely because we're fetching a large amount of data from the database and then tying that all together in Julia. And it needs to match certain distributions. So that's what we'd show the customer. And then we can do time series, but there's obviously, visually we can tell that there's something wrong with this time series. Right? There's this real little peak over here that it looks like it's out of bounds, but if we look at data over time, this is fairly close to the peak that we would expect in a day. The problem is it's not an expected peak at this time of the day. I've taken out the time values because it doesn't matter for this presentation, but we might see this kind of a peak, but we might not see it so sharp. We might see it more smoother. We might see it get up there and then slowly taper off. So it shouldn't be expected at this time of the day. And unfortunately, Java is not that good at looking at all of this past data and saying, this thing does not look right, the way that you and I can look at it visually and say, this thing does not look right. Right? We have a much stronger processor than would be written in Java. So the Java process has a sliding window. It stores a small amount of data in memory, just what's required to visualize. So over here, it would have that much data in memory. And it can't look back in time very quickly to tell you that this thing should not have been there. It's used for dashboards, used for API calls, and alerts. But like I said, it doesn't know anything back in time, so you would have to tell it what to alert on. Right? I could tell it, alert me if everything went above this level. But on the course of a normal day, could be a Wednesday, could be a Thursday, I might expect my normal traffic to be there. So that's not something I can just tell Java to say, alert me when traffic goes above this level. It's good at applying a set of quick arithmetic rules, not so good at figuring out the rules on a large data set. So that's where we wanted to bring in Julia. Because Julia is great at processing large amounts of data, especially columnar data. So even though we have 500 different dimensions, we may not need to look at all of them to determine what the expected values are. We can look at a few of the columns together and figure out what's normal and what's not. It's good at doing matrix multiplications, again, because we can do them columnar. There are already modules for doing Fourier analysis. So especially with time series data, it's cyclic in nature. You do Fourier analysis, essentially treat it like a digital signal, and you figure out the different components of that. You can do regression analysis, hypothesis testing, curve fitting. All of that is very easy with very little code in Julia. Right? You can also try out multiple algorithms in parallel. So you can start up a thread and say, I'm going to test out this algorithm with the data, this algorithm, and run them all, and then see which one gets me my best fit. And then tell Java, you know what, this algorithm worked well for this customer's data set, for this particular metric that you're looking at. And so go ahead and use that. But it's not something we want to start up on every request. We keep talking about time to first plot. That is come down a lot, but it's still measured in order of seconds. Whereas we need responses in the order of microseconds or milliseconds. Right? So I cannot start up a Julia process on every request to figure out whether something is an anomaly or not. I want to be able to do this over a longer period of time and then tell my Java process that's already running, when you see something that's out of this pattern, that's something to alert on. So remember this diagram that we had earlier, we essentially added this little component. So did not change the architecture too much, but we added our anomaly modeler in here, which essentially takes now all of the data which comes in. So through the stream, it also gets fed to the anomaly modeler. And that thing looks at multiple algorithms 4 different metrics that the customer cares about. And when it figures out the right algorithm, it'll tell mPulse, go ahead and use this particular algorithm. So it could be as simple as this is the expected IQR of a minute, right? So you get all of these data points for a minute, which could be, let's say, 1,000, 10,000 data points in 1 minute. Just do your P75 and P25 on that, figure out the IQR. And if things are outside a certain range, then that is an anomaly. That's an alert to be fired. Or it could be a more complex thing where it gives you the entire, let's say KNN ICAD is another algorithm we'd use, where you'd have the matrices that you need to multiply and then tell Java, go ahead and apply that only on the small data set of 1 minute rather than looking at 1 month of data. And so Java can do that kind of small amount of data processing very quickly. But it needs to know which one to use and on what data set to use it. So that's where we tie the two together. And so what we end up with is a better, I don't know if it's visible, but there are bands here. So what our anomaly modeler has done is for the same data set, it said you have an upper bound and a lower bound of the expected values of the data for every minute of the day. Right? And this might change for weekdays and weekends. It might change for repeated events, holidays and stuff like that. And so this event that happens here is out of bounds because the bound is over here for this point of time, whereas the bound is up here for that point of time. And so this is an anomaly at this point of time, and it's fired an alert. Now we'd also notice may not be very clear, but there are like 2 points there where it kind of stretches to the edge and might be exceeding the bounds. But the other thing is that you might exceed the bounds for 1 minute, but that's not necessarily an anomalous event because it could be something that's unique to this day. Whereas if you exceed the bound for multiple minutes in a row, then that's more like an anomaly. So in this case, we have 1, 2, 3, probably 5 minutes when it's exceeded the bounds, and therefore we define it as an anomaly. And so this is the kind of things that this visualization would have been done in Julia versus this visualization which is done in Java. So this is all this is doing is taking the count star over time and plotting that, right? This is doing this count star over time plus figuring out the IQR for multiple months of data and plotting all of those together on the same chart. So if we zoom in a little more, this is more about the details of how we did the architecture. So we already had Jupyter. We were using notebooks to do a lot of our analysis. So we said, why not reuse Jupyter to do this? But we don't want to allow arbitrary code to be sent through Jupyter. Right? Jupyter will allow you to type in any code and it'll send that to a Julia kernel, which will execute it. We don't want the customer or somebody who has access to that to send arbitrary code through a web service that runs on our server with our data. So we modified Jupyter a bit where it only accepts JSON. Right? You can send it configuration saying, I care about this particular customer's data, and we can use authentication to figure out whether the person requesting it has access to that data. And then I care about these particular fields. I want to see data from Chrome, from this particular country, and I just want to look at the page load time, or I want to look at the total traffic. And so what Jupyter will do is it'll start up a Julia kernel, and it'll pass all this configuration back over to Julia. Julia will say, okay, thank you, I've received that. Please let the mPulse know that I am going to start processing it, and that's it. So it's send the request over, and then the response back is saying, yes, I've got it. Once that happens, the Julia process may or may not start up multiple threads to run multiple algorithms in parallel. Look at the data. Given the filters, it'll look at past data and try and figure out the different parameters for the models. And once it has figured that out, which might take, in the fast case, it might take a few minutes. The slow case, it might take up to 6 hours. And nobody cares because nobody is waiting for it to respond. Right? It'll tell mPulse, I'm done with this. This is what you should do to figure out if there's an anomaly or not. And now mPulse already has that data stream in memory, so it can immediately start applying those rules. It might have 1 hour's worth of data already, but it only needs to look at the latest minute. So it'll say, all right, let's apply these rules to the latest minute and see was there an alert or not. So from the time to defining something as I want to be alerted on this, to actually being alerted, it could be pretty quick, a couple of minutes for the first alert, right? After that, it'll just keep happening automatically. Or it could be a couple of hours. And then the model will retrain itself every couple of weeks. So your data traffic might change over time, and it can retrain itself. So you don't need to know that it's retraining, because it'll take whatever time it needs to retrain, use the old model until the retrain is complete, and then run the new model as soon as that is complete. Yeah, and then finally, mPulse can send alerts in various ways, either using email or using Slack or calling a webhook or something else. So by doing this, we avoid code injection, right? I said our Julia application receives a JSON configuration, which checks to see if the keys and types of the elements in the JSON object match the method values. So we built a module called Method Inspector. Again, you can package add that. It's in the Julia repository. It essentially has 4 methods, right? Arg names, arg types, KW args, and KW types. You pass it a method, so not a function, but a method of a function, and it'll tell you the names of the positional arguments, the types of the positional arguments, or the names of the keyword arguments, and the types of the keyword arguments. And so we use that a lot to do this kind of introspection to figure out which method or whether a method exists at all, right? When you pass in the JSON, does a method exist that can do that kind of modeling that has been requested by the JSON? And by doing it this way, we can update the Java code independently of the Julia code, and the Julia code independently of the Java code. So we discard anything that is unknown by the Julia side, and similarly, when we write back to the Java side, that can use or discard anything that it doesn't know about. We could, I think, probably in a nowadays we could probably do that with Pluto, but Pluto didn't exist when we first wrote that. So the development process, and I'm kind of coming to the end of the talk here, but with the development process, we have our data scientists who develop all the algorithms for doing the anomaly detection. It's not a job that software engineers need to worry about. But software engineers need to worry about memory allocation and getting the algorithm to run fast in Java and being able to distribute it across multiple hosts. So once the data scientists have figured out the algorithm, built a proof of concept, and run it for a while, again, we can run it on a notebook server, or we can run it independently of the existing model. Then they will work with the software engineers to cut down that algorithm. So you may not need the full algorithm, right? An algorithm you're running on multiple months of data may be simplified to run on 1 minute's worth of data. So they will work with the software engineers to figure out the minimum viable algorithm for that amount of data that it needs to look at, and say, all right, go ahead and implement this as efficiently as you possibly can to run in microseconds or milliseconds in memory. And then they define a specification saying, okay, this is how I'm going to send you the model. This is how you're going to request for a model. And at runtime, an algorithm is only used if both components support it. So for example, we could upgrade the Julia side to support new algorithms, but those algorithms will never be sent back to the Java side, because the Java side essentially tells the Julia side, I need a new model, but these are the only algorithms I understand. So give me one of these algorithms. But we can use it to test on production data, because we're not dependent on, don't need to send the new models back to the production system. And then once Java has been upgraded, it'll automatically start sending the new models if they're better, right? And similarly, we can deprecate all models in the same way. We can upgrade the Julia to stop supporting a particular model, and then it'll just no longer send that to Java. So in summary, as with bread, preparing the model takes way more time than consuming it, right? We need hours, minutes to hours to process the data, but we have microseconds to milliseconds to actually run on that data. You need to use the right tool for each step of the way. So in this case, we have Java that has everything in memory, that does a lot of jobs together. But we have Julia to do a lot of the heavy lifting that Julia is good at doing, that Java may not be good at doing. You need to communicate your process. So the two components need to be able to define a protocol that they're going to use to exchange data between each other. And finally, allow function calls to be mapped to JSON. I'd like to thank all of these modules on that side. The Julia Starts module, or it's a organization. We use pretty much everything from there. Also DSP, data frames, data structures, and Julia itself. And there's a bunch of modules that we have released on our own. These slides are on pre-talks, so you don't need to copy that. You can download the slides and look at them. Thank you.
Any question? Yeah.
Hi, thanks. Could you elaborate on the methods you use for the anomaly detection?
Yeah. So I guess let me go back to the slide. So in this particular case, so we've used just a basic IQR method. So you have your time series over time, or your data over time, and we will look at by minute over multiple months and decide for each minute of the day. There are, we call it the IQR method, but there are various things to look at. So there's trending, and the data may trend up or down over time. So you need to figure out the trend line. Then there's seasonality, so that's why we'll use Fourier analysis to figure out the seasonality. Once we figure out those two components, we will extract them from the data. So we'll define the parameters. For trend, it's essentially a linear regression, so you get your y equals mx plus c. If you figure out your m and the c, you can store that in your model. Then you're the same with your Fourier analysis. You figure out the different frequency components and store that in your model. And then you're left with noise. Right? And that noise is your actual randomness over the course of time. So you figure out the IQR for that, the different percentiles. And you could have a tolerance. The customer might say, I want to be very sensitive, or I might want to be less sensitive. Or I might want to be very sensitive for these times of the day and less sensitive for these times of the day. So you can change your IQR bandwidth based on that sensitivity. And then when the Java process gets the same, it can apply the trend lines and the seasonality to what it has, and then look at the IQR of what's left over. Other cases, like I mentioned, is CAN and ICAD. That is a little more complicated to explain as an answer. There is a large research paper on that you can look it up. It's just called K nearest neighbors. I forget what the ICAD part stands for. So the clustering, there is Holt-Winters, triple exponential smoothing, another way of doing it. Yeah. Does that answer your question? All right. Any other questions?
Yeah.
What do your customers do with alerts when you trigger them?
All right. Yeah, that's a good question. So, yeah, alerts are useless if you don't do anything about it, right? One of the reasons for anomaly detection is customers need alerts. They need to know if traffic is going spiking beyond. Now, in this case, it's traffic. They may not care so much if traffic is going up. That may be a good thing. They do care if performance is going down, right? So if the load time is going up, that's something they want to be alerted on. Or if the time between a user clicking on something and the page responding takes too long. Or if the number of purchases have dropped, or the number of times a user converts has dropped. Those are the things they want to know about pretty immediately. Even if it's at 4 a.m., they want to know users normally buy, let's say, $1,000 worth of stuff right now, but they're only buying $100 today. So that's something you want to wake up for and check. Maybe something on your server is broken or something else. We can tie that together. So this is just looking at one metric, but we can look at other metrics and do correlation analysis on that and say, hey, you got alerted on this, but these are the other things that also changed at that time. So they could be related, and then they can be actionable. So the person who gets woken up with a page can decide whether he needs to escalate it or not. And generally, the sensitivity and stuff for different metrics, they might have different sensitivity values. There's also, like in the case of traffic, or let's say in the case of performance, you might care if the performance got worse, but not if it got better. So the bands, we can say ignore the lower end of the band. So even if it goes below the lower end, don't alert me. But I want to know the next day. So it'll send you an email that you can check in the morning. Maybe something went wrong, right? So sometimes a really fast page is a page with no information on it because it didn't load at all. So it might show up as really fast, but it's broken. We can look at JavaScript errors as well. That's another metric that they would look at. Yeah, but it's looking at what users are doing. So it only tells you that something a user tried to do broke, or something is going to break, like traffic is going up and your servers may not be able to handle that load.
All right, thank you. Any
Okay.
other questions? If not, then I have another question.
Yeah.
So in your model, you need to train it first, right?
Yeah.
Using available data.
Yeah.
I was wondering, do you need to train with same type of data from the same customer, or
Yeah.
you can reuse, let's say, already trained model for them?
No, we always do it same customer. It's mainly for privacy. We don't want to share data across customers, but also customers might have custom metrics and timers that only make sense for that customer. So like the same timer field might have a different meaning for different customers. So we can't use it across customers. What we can do is when we're doing broad research across the industry, we can say, let's look at all e-commerce customers together, or look at all financial institutions, or all newspapers, and look at as a whole, what does the industry look like, and then how does each customer compare to that. So those are things we can do, but we don't do that. So we don't offer that directly to customers. That's something we would do independently on our own research.
I see. Thank you. And how much data? Like you need, let's say, if you want to predict 1 hour, you need like a 1 week of data or so?
Yeah, well, so typically we say 2 weeks because you want at least 2 weekends. If you have 1 weekend, it's not enough to figure out a trend, the weekend cyclicity. So 2 weeks is the minimum that we recommend. It can go up to 13 months of data. We don't store longer than that, again, for privacy issues. We intentionally age out data after 13 months.
Okay, all right. Thank you. That concludes this session. Thank you.
All right, thank you.